Hey guys, welcome to the Ethereum Whitepaper Part 2. Let's dive in. The term transaction is used in Ethereum to refer to the signed data package that stores a message to be sent from an externally owned account. Transactions contain the recipient of the message, a signature identifying the sender, the amount of ether to transfer from the sender to the recipient, an optional data field, a start gas value representing the maximum number of computational steps the transaction execution is allowed to take, and a gas price value representing the fee the sender pays per computational step. The first three are standard fields expected in any cryptocurrency. The data field has no function by default, but the virtual machine has an OP code which a contract can use to access the data. As an example use case, if a contract is functioning as an on-blockchain domain registration service, then it may wish to interpret the data being passed to it as containing two fields, the first field being a domain to register and the second field being the IP address to register it to. The contract would read these values from the message data and appropriately place them in storage. The start gas and gas price fields are crucial for Ethereum's anti-denial of service model. In order to prevent accidental or hostile infinite loops or other computational wastage in code, each transaction is required to set a limit to how many computational steps of code execution it can use. The fundamental unit of computation is gas. Usually, a computational step costs 1 gas, but some operations cost higher amounts of gas because they are more computationally expensive, or increase the amount of data that must be stored as part of the state. There is also a fee of 5 gas for every byte in the transaction data. The intent of the fee system is to require an attacker to pay proportionately for every resource that they consume, including computation, bandwidth, and storage. Hence, any transaction that leads to the network consuming a greater amount of any of these resources must have a gas fee roughly proportional to the increment. Contracts have the ability to send messages to other contracts. Messages are virtual objects that are never serialized and exist only in the Ethereum execution environment. A message contains the sender of the message, implicit, the recipient of the message, the amount of ether to transfer alongside the message, an optional data field, a start gas value. So essentially, a message is like a transaction, except it is produced by a contract and not an external actor. A message is produced when a contract currently executing code executes the call opcode, which produces and executes a message. Like a transaction, a message leads to the recipient account running its code. Thus, contracts can have relationships with other contracts in exactly the same way that external actors can. Note that the gas allowance assigned by a transaction or contract applies to the total gas consumed by that transaction and all sub-executions. For example, if an external actor A sends a transaction to B with 1000 gas, and B consumes 600 gas before sending a message to C, and the internal execution of C consumes 300 gas before returning, then B can spend another 100 gas before running out of gas. And here we have the Ethereum state transition function. And here we learn how the Ethereum state transition function can be defined. Number 1, check if the transaction is well formed. For example, it has the right number of values. The signature is valued and the number once matches the number once in the sender's account. If not, return an error. Calculate the transaction fee as start gas times gas price and determine the sending address from the signature. Subtract the fee from the sender's account balance and increment the sender's number once. If there is not enough balance to spend, return an error. Initialize gas equals start gas and take off a certain quantity of gas per byte to pay for the bytes in the transaction. Number 4. Transfer the transaction value from the sender's account to the receiving account. If the receiving account does not yet exist, create it. If the receiving account is a contract, run the contract's code either to completion or until the execution runs out of gas. If the value transfer failed because the sender did not have enough money or the code execution ran out of gas, revert all state changes except the payment of the fees and add the fees to the miner's account. Number 6. Otherwise, return the fees for all remaining gas to the sender and send the fees paid for gas consumed to the miner. Here we have an example that supposes that the contract code is as follows. Note that in reality the contract code is written in the low-level EVM code. This example is written in Serpent, one of our high-level languages, for clarity, and can be compiled down to EVM code. Suppose that the contract storage starts off empty and a transaction is sent with 10 ether value, 2000 gas, 0.001 ether gas price, and 64 bytes of data, with bytes 0 to 31 representing the number 2 and bytes 32 to 63 representing the string. The process for the state transition function in this case is as follows. Number 1, check that the transaction is valid and well formed. Number 2, check that the transaction sender has at least 2000 multiplied by 0.001 equals 2 ether. If it is, then subtract 2 ether from the sender's account. Initialize gas equals 2000. Assuming the transaction is 170 bytes long and the byte fee is 5, subtract 850 so that there is 1150 gas left. Subtract 10 more ether from the sender's account and add it to the contract's account. Number 5, run the code. In this case, this is simple. It checks if the contract storage at index 2 is used, notices that it is not, and so it sets the storage at index 2 to the value Charlie. Suppose this takes 187 gas, so the remaining amount of gas is 1150 minus 187 equals 963. Add 963 multiplied by 0.001 equals 0.963 ether back to the sender's account and return the resulting state. If there was no contract at the receiving end of the transaction, then the total transaction fee would simply be equal to the provided gas price multiplied by the length of the transaction in bytes, and the data sent alongside the transaction would be irrelevant. Note that messages work equivalently to transactions in terms of reverts. If a message execution runs out of gas, then that message's execution and all other executions triggered by that execution revert, but parent executions do not need to revert. This means that it is safe for a contract to call another contract, as if A calls B with G gas, then A's execution is guaranteed to lose at most G gas. Finally, note that there is an OP code, create, that creates a contract. Its execution mechanics are generally similar to call, with the exception that the output of the execution determines the code of a newly created contract. Code execution. The code in Ethereum contracts is written in a low-level stack-based bytecode language referred to as Ethereum Virtual Machine Code, or EVM code. The code consists of a series of bytes where each byte represents an operation. In general, code execution is an infinite loop that consists of repeatedly carrying out the operation at the current program counter, which begins at 0, and then incrementing the program counter by 1 until the end of the code is reached of an error or stop or return instruction is detected. The operations have access to 3 types of space in which to store data. The stack, a last in first out container to which values can be pushed and popped. Memory, an infinitely expandable byte array. The contract's long-term storage, a key value store. Unlike stack and memory, which reset after computation ends, storage persists for the long term. The code can also access the value, sender, and data of the incoming message, as well as block header data, and the code can also return a byte array of data as an output. The formal execution model of EVM code is surprisingly simple. While the Ethereum virtual machine is running, its full computational state can be defined by the tuple as follows, where block state is the global state containing all accounts and includes balances and storage. At the start of every round of execution, the current instruction is found by taking the PCTH byte of code, or 0 if PC, and each instruction has its own definition in terms of how it affects the tuple. For example, add pops 2 items off the stack and pushes their sum, reduces gas by 1, and increments PC by 1. And store pops the top 2 items off the stack and inserts the second item into the contract storage at the index specified by the first item. Although there are many ways to optimize the Ethereum virtual machine execution via just-in-time compilation, a basic implementation of Ethereum can be done in a few hundred lines of code. Blockchain and mining. The Ethereum blockchain is in many ways similar to the Bitcoin blockchain, although it does have some differences. The main difference between Ethereum and Bitcoin with regard to the blockchain architecture is that, unlike Bitcoin, which only contains a copy of the transaction list, Ethereum blocks contain a copy of both the transaction list and the most recent state. Aside from that, two other values, the block number and the difficulty, are also stored in the block. The basic block validation algorithm in Ethereum is as follows. Number 1, check if the previous block reference exists and is valid. Number 2, check that the timestamp of the block is greater than that of the reference previous block and less than 15 minutes into the future. Number 3, check that the block number, difficulty, transaction root, uncle root, and gas limit, or various low-level Ethereum-specific concepts, are valid. Number 4, check that the proof of work on the block is valid. Number 5, let the following code be the state at the end of the previous block. Number 6, let more code be the block's transaction list with n transactions. If any application returns an error, or if the total gas consumed in the block up until this point exceeds the gas limit, return an error. Number 7, let the following code be more code, but adding the block reward paid to the miner. Number 8, check if the Merkle tree root of the state s_final is equal to the final state root provided in the block header. If it is, the block is valid, otherwise it is not valid. The approach may seem highly inefficient at first glance because it needs to store the entire state with each block, but in reality, efficiency should be comparable to that of Bitcoin. The reason is that the state is stored in the tree structure, and after every block, only a small part of the tree needs to be changed. Thus, in general, between two adjacent blocks, the vast majority of the tree should be the same, and therefore the data can be stored once and referenced twice using pointers, for example, hashes of subtrees. A special kind of tree, known as a Patricia tree, is used to accomplish this, including a modification to the Merkle tree concept that allows for nodes to be inserted and deleted and not just changed efficiently. Additionally, because all of the state information is part of the last block, there is no need to store the entire blockchain history, a strategy which, if it could be applied to Bitcoin, can be calculated to provide 5 to 20 times savings in space. A commonly asked question is where contract code is executed in terms of physical hardware. This has a simple answer. The process of executing contract code is part of the definition of the state transition function, which is part of the block validation algorithm. So if a transaction is added into block B, the code execution spawned by that transaction will be executed by all nodes, now and in the future, that download and validate block B. In general, there are 3 types of applications on top of Ethereum. The first category is financial applications, providing users with more powerful ways of managing and entering into contracts using their money. This includes subcurrencies, financial derivatives, hedging contracts, savings wallets, wills, and ultimately even some classes of full-scale employment contracts. The second category is semi-financial applications where money is involved, but there is also a heavy non-monetary side to what is being done. A perfect example is self-enforcing bounties for solutions to computational problems. Finally, there are applications such as online voting and decentralized governance that are not financial at all. Token systems. On-blockchain token systems have many applications ranging from subcurrencies representing assets such as USD or gold to company stocks, individual tokens representing smart property, secure unforgeable coupons, and even token systems with no ties to conventional value at all, used as point systems for incentivization. Token systems are surprisingly easy to implement in Ethereum. The key point to understand is that a currency or token system fundamentally is a database with one operation: subtract X units from A and give X units to B, with the provision that, number 1, A had at least X units before the transaction, and number 2, the transaction is approved by A. All that it takes to implement a token system is to implement this logic into a contract. The basic code for implementing a token system in Serpent looks like the following. This is essentially a literal implementation of the banking system state transition function described further above in this document. A few extra lines of code need to be added to provide for the initial step of distributing the currency units in the first place, and a few other edge cases. And ideally, a function would be added to let other contracts query for the balance of an address. But that's all there is to it. Theoretically, Ethereum-based token systems acting as subcurrencies can potentially include another important feature that on-chain Bitcoin-based metacurrencies lack: the ability to pay transaction fees directly in that currency. The way this would be implemented is that the contract would maintain an Ether balance with which it would refund Ether used to pay fees to the sender, and it would refill this balance by collecting the internal currency units that it takes in fees and reselling them in a constant running auction. Users would thus need to activate their accounts with Ether, but once the Ether is there, it would be reusable because the contract would refund it each time. Financial derivatives and stable value currencies. Financial derivatives are the most common application of a smart contract and one of the simplest to implement in code. The main challenge in implementing financial contracts is that the majority of them require reference to an external price ticker. For example, a very desirable application is a smart contract that hedges against the volatility of Ether or another cryptocurrency with respect to the US dollar. But doing this requires the contract to know what the value of ETH to USD is. The simplest way to do this is through a data feed contract maintained by a specific party, for example NASDAQ, designed so that the party has the ability to update the contract as needed, and providing an interface that allows other contracts to send a message to that contract and get back a response that provides the price. Given that critical ingredient, the hedging contract would look as follows. Number 1, wait for party A to input 1000 Ether. Number 2, wait for party B to input 1000 Ether. Number 3, record the USD value of 1000 Ether calculated by querying the data feed contract in storage. Say this is $X. Number 4, after 30 days, allow A or B to reactivate the contract in order to send $X worth of Ether calculated by querying the data feed contract again to get the new price to A and the rest to B. Such a contract would have significant potential in crypto commerce. One of the main problems cited about cryptocurrency is the fact that it's volatile. Although many users and merchants may want the security and convenience of dealing with cryptographic assets, they may not wish to face that prospect of losing 23% of their value in their funds in a single day. Up until now, the most commonly proposed solution has been issuer-backed assets. The idea that an issuer creates a subcurrency in which they have the right to issue and revoke units, and provide 1 unit of the currency to anyone who provides them offline, with 1 unit of a specified underlying asset, such as gold or USD. The issuer then promises to provide 1 unit of the underlying asset to anyone who sends back 1 unit of the crypto asset. The mechanism allows any non-cryptographic asset to be uplifted into a cryptographic asset, provided that the issuer can be trusted. In practice, however, issuers are not always trustworthy, and in some cases the banking infrastructure is too weak or too hostile for such services to exist. Financial derivatives provide an alternative. Here, instead of a single issuer providing the funds to back up an asset, a decentralized market of speculators betting that the price of a cryptographic reference asset, such as Ether, will go up, plays that role. Unlike issuers, speculators have no option to default on their side of the bargain because the hedging contract holds their funds in escrow. Note that this approach is not fully decentralized because a trusted source is still needed to provide the price ticker, although arguably even still this is a massive improvement in terms of reducing infrastructure requirements. Unlike being an issuer, issuing a price feed requires no licenses and can likely be categorized as free speech, and reducing the potential for fraud. Identity and reputation systems. The earliest alternative cryptocurrency of all, Namecoin, attempted to use a Bitcoin-like blockchain to provide a name registration system where users can register their names in a public database alongside other data. The major cited use case is for a DNS system, mapping domain names like bitcoin.org, or in Namecoin's case, bitcoin.bit, to an IP address. Other use cases include email authentication and potentially more advanced reputation systems. Here is the basic contract to provide a Namecoin-like registration system on Ethereum. And here we see the code. The contract is very simple. All it is a database inside the Ethereum network that can be added to. but not modified, removed. Anyone can register a name with some value, and that registration then sticks forever. A more sophisticated name registration contract will also have a function clause allowing other contracts to query it, as well as a mechanism for the owner, or the first register of a name, to change the data or transfer ownership. One can even add reputation and web of trust functionality on top. And with that, guys, we are gonna take another break.